the output will be water vapors. Okay. So means if you are burning as a with a clean oxygen, it will be a clean fuel. So there will be no emission. So the my today's topic, okay, you may little bit feel slightly deviating from marine or ship technology, but ultimately in the ship also to run the ship, we need energy, and for that also we are using the fossil-based fuels, or nowadays we have uh, the fuel cell-based engines we have, and maybe in the future you are going to use the engines which will be directly running with the hydrogen as a fuel. Okay. So if we if we try to concentrate on that part, so you will be getting a good information from my talk on that particular category. So whenever when if I used to say that I'm working on hydrogen, or when I start giving my talk on hydrogen, so the very first impression you may be having that I'm going to talk about the fuel cells, how we're going to use fuel cell using hydrogen, or how we are going to use uh, the IC engines, the combustion of hydrogen. But uh, the thing is, I am not working on the same these two topics. So apart from these two topics, there is a big area for hydrogen where we have to find out the solutions. Until we don't have the solutions that side, we cannot come to the combustion or fuel cell. Okay. Anyway, in my slides, I'm going to show you just a brief I am giving. Okay. So just small brief. Then only if I start talking about this, you will able to recollect. Okay. So if it is a fuel cell or if it is a combustion, in both the cases, any of the vehicle which is running with the energy, okay, burning of fuel or maybe fuel cell. So it may be a combustion engines or maybe fuel cell. In both the cases, the requirement is hydrogen. Okay. So if many places already we have tested that fuel cell efficiently working with hydrogen, IC engines also with 100% hydrogen, it is working. Even many companies, they started working on development of the gas turbines working with pure 100% hydrogen. So that is possible. But before going for this application of combustion or fuel cell, if you just go one step back, the very important area is the storage. That is a major concern in the technology of hydrogen. Because this is a dangerous, it is like a hydrogen bomb. If you are keeping hydrogen in any of the place at a high pressure, it is a kind of bomb only. So, like if you have gone through the workshops in our colleges, okay, so small this size cylinder we used to use in a welding or other applications. If that cylinder we are keeping with hydrogen, that is sufficient to blast one complete building also. That is highly dangerous. So the same thing if you are going to keep on a ship or maybe on other automotive vehicles, so that is like a uh, running bomb in a open market. Okay. So to safeguard this or to make it working safely, the very important area here is a storage. So some of the points I'm going to discuss on the storage of that. For storage also we have multiple options that I'm going to discuss again. Apart from that, if somehow we can able to got the technology, okay, we can able to uh, safely store at high pressure. High pressure means I'll tell you the projected on-board application pressure is 700 bar. Means to run a vehicle, on-board vehicle, okay, the hydrogen should be minimum of 700 bar pressure, then it can come to the market. So uh, since we have all the students from engineering background, you know how much will be the 700 bar pressure. That is huge. And also to achieve that pressure, how much energy is required, because for compression of any of the gas, huge amount of energy is required. So here we're going to discuss some other alternate also to replace the conventional compression process to achieve high pressure of hydrogen storage that can be applied to fuel cell or combustion. Okay. So that's why I'm telling this may little deviate to your stream, but ultimately it's a part of the ship. So this slide already I discussed in a brief that there is a huge need of to find alternate option for future that should be clean. Okay, because when we talk about sustainability, now each and every sector, it may be energy or manufacturing, everywhere, so the term sustainability will be always there. So in simple language, if you want to understand what is sustainability, so that is the thing. Presently, we have to work in such a way that should not affect our third generation. Okay. So if our generation is working something for future, so we have to think about my son and his son. So that generation should not affect with our technology, because many a times lot of technology we are talking about, and currently it is showing it is excellent, but at the end it will be producing a problem to the next generation. Okay, the same problem is identified now. The many work is going on that lot of EV vehicles we are planning about that. After 100 years, all these batteries will be going to cause a lot for land pollution. So that's why now again people have started working how to uh, this replace the batteries. It should be eco-friendly and all. So the example is we have to talk in such a way it should not affect the third generation. So here for this, for the requirement of the future energy solutions, so we have a lot of options. You can see here. So we have solar, hydro, many are there. Okay, and they are good enough. The problem with some of these uh, uh, the technologies like solar, if you take, it is an intermittent. Okay, so solar we cannot have always. Means okay, daytime we can able to extract lot of energy, but it comes to the evening time, then there is no energy source, and somehow we have to work on the storage part. Okay, that again it is a next thing. So there should be like currently if you have diesel or if you have gasoline fuel, so it is day or night, whenever you want it's available to produce energy. So kind of thing we should have some option which can able to produce energy anytime. So in that case, you can able to say hydrogen can be an option if you want to come for combustion, anytime it is ready. Other application also, what we'll discuss, it is ready for anytime. The only thing is we have to talk about its feasibility and safe. Safety is very important for hydrogen. So these are the reasons why people like me talking about the hydrogen. Okay, it is abundant. So since we have plenty of water, and if we have good enough technology to split water into H2 and O2, we can able to generate a good amount of hydrogen. Okay, it is having a high energy density. So in a simple language, I can tell you, it is having more than 3 times energy than the diesel or petrol. Okay, so we can able to extract a huge amount. Regenerative, the example is fuel cell. Okay, fuel cell takes H2O2 separately and coming out as a water. Even if you are doing the combustion at a clean oxygen, it will be a water vapors. So it can be the cycle is complete. In the case of hydrogen, the cycle is complete. It starts from water, it comes out as a water. And obviously it's eco-friendly in the case of fuel cell and combustion in a pure oxygen. Okay, when we are burning the hydrogen with air. Okay, so because when we are going to drive the vehicle, any of the engines, we are not going to carry separately one tank for oxygen. It will be taken from the air only. In such case, there will be a chances for NOx production. Okay. But the thing is, the amount of NOx produced by these systems will be very, very, very low compared to the current gasoline and diesel combustions. So out of this many advantages, okay, the big challenge we have is low volumetric density. Okay, since it is the smallest gas, okay, in our periodic table, we can say this is the first element in our table, the smallest gas. So its volumetric density is very low. Okay, so that is a demerit, but again, we have solutions that obviously any of the gas, if you want to increase the density, we can able to compress it. So by compressing, we can increase it, and it's going on. So when we talk about the combustion or anywhere, any application, compressed hydrogen we are using. It is compressed. We are compressing it to store more mass in a small volume. That is going on. So we can able to increase density. Okay. We'll talk this topic again later. Then we can able to store in a low temperature. Okay. If we are reducing the temperature to very low, okay, like 77 Kelvin, we can able to liquefy the gas. So again here, if you liquefy, we can able to store, we can able to increase its volumetric density. After that, one more option is there, that is the storage in a solid form. So here we are not going to convert the gaseous hydrogen into solid hydrogen. Here the thing is there are several materials available which can able to absorb hydrogen. So in that form, we can able to convert the, or we can able to store hydrogen into the solid form. So now lot of work is going on in this topic, because if we see the different options of storage, okay. So in the compared to gaseous form, compressed gas form or liquid form, there's always a high risk of leakage. Okay, because it is a minute, it is a smallest gas, and it can come from a minute leakage also. And in both the cases, if you are using very high pressure storage, there is always a, it will be prone to leakage. And if you are keeping in a low temperature, and because of the temperature difference, it will boil off and it can leak. Okay, so the compression storage and liquid storage both are very good. It's going on, many places going on, but only one risk that we have to work on, that is the leakage, and that may go to the explosion. That itself, if you want to, if you go to the third option in the solid storage option, here we can completely remove that risk. So in that form, when we stored hydrogen in a gaseous, in a solid form on the materials, there will be no risk of leakage, because it is going to absorb in the interstitial sides of the material. So until we supply heat to the material, it will not release the gas. So it is the safest mode. As of now, out of these three, it is called as the safest mode of storage. So in case of storage, if you want to go, it will be the best option. So my today's talk will be more about that third category of storage of hydrogen on a solid form. Once it is stored in a solid form, okay, you can integrate this with fuel cell, integrate with IC engines. So it will solve the problem of storage here, and you can able to use anywhere. Some examples I will show. So majorly when we talk about the hydrogen, so we'll be having main three challenges. Okay, those are still unsolved. The production, storage, and application. Okay, somehow we have the options that where we can able to apply. Like I told, we can use successfully in a fuel cell. Combustion also, we have gone to that much level of research. We can able to use in IC engines. Okay, it can be used in a gas turbines to produce electricity. So application part, now we are clear. What are the different sectors where we can able to use hydrogen successfully to fulfill the future needs? Still, the problem persists with the production and storage. Okay. Again, I listed some 3-4 names here, the methods of production. These are not limited. We have many sources to produce hydrogen. Maybe next slide, I will show you the options. Okay. Out of this, many options, some 7-8 options are there. Okay. Out of all these, the first option, that is electrolysis of water, that only gives the pure hydrogen. Other any of the source, if you take, okay, it is not coming out as a pure hydrogen. There will be always a possibility of CO and CO2. And again, our purpose is to reduce those. Okay. So still in the different methods of production, people are working to reduce those gases, or after producing, they are working to capture those gases to produce pure hydrogen. But when we go for the electrolysis of water, they are giving the pure as now as far as the purest form. Still the lot of research going on the membrane side, the electrolyte side, okay, the electrode side, to increase the rate. Okay, we can able to produce, but the rate is still, if we can go for the more production rate. Okay, so that is going on. So that's why I'm saying still there is a challenge for in the section of production. Storage, obviously, the problem is still there because uh, as of now, we got success to build cylinders called Type 4, Type 5 cylinders. Okay, when we say Type 4 cylinders, those are the cylinders which can able to work safely till 700 bar pressure. When we say Type 5 cylinders, those are the cylinders which can able to successfully work at 900 bar pressure. Okay, so the technology we develop, we can able to make also, but it's going very high. It's very costly. Okay, so when we going to implement those for the big applications, like we're putting in industries, that will be good. But when we want to go for the onboard applications, mobile applications, for small car, if you want to use hydrogen, in that case, if you are going to purchase 10 lakh rupees only cylinder, the vehicle cost will be very, very high. So still there is a people are there working on the material side to reduce the cost of the tanks which can able to sustain that much high pressure. Okay. So in both the cases, we have this challenge for liquid and compressed gas. The solid state, okay, that as I mentioned, it is the safest mode as of now. So that we'll discuss in detail in the further slides. And apart from that, storage of hydrogen on that solid form, I'm going to tell you a very good application of that material, which can which has the potential to completely replace the mechanical compressor. That will be my main topic, to produce compressed hydrogen for our fuel cell or combustion applications. Okay. Then application, somehow we have the data. Okay. These are some of the hydrogen production methods, just for the information I'm putting. Okay. So the produced hydrogens are categorized based on some colors. Okay. The colors are not a color of the gas. The colors are based on the production method. Okay. So when we say green hydrogen, okay, so nowadays we are talking about the clean and green energy, clean fuel. So here when we say green hydrogen, which means during the production of hydrogen, there should be no other greenhouse gas should come. Okay, if there is no CO2 and only H2 is coming, then we can say only green hydrogen. That's why I told in the case of electrolysis, if you see here, so in the case of electrolysis, this is the only option we have which is producing pure hydrogen without any other gases involved. So we can say it's a green, but still here there is a potential to increase the production rate. Other, if you see gray, blue, brown, black, many are there based on their production method. Okay, so all the other methods, if you use, there will be a production of CO, NOx, CO2 is there, methane is there. Okay, so based on those categories, some color codings are there. So here, huge scope is there to produce green hydrogen with other methods also. It's working. I think this video is not working. Okay, no problem. So now this we have seen the production of hydrogen. Now there's a storage methods. As I mentioned, we can store in a these are the tanks. These are the some example of tanks I told. Okay, such type of tanks, the compact and lightweight uh, cylinders we or tanks we have to make, which can able to sustain high pressure. Okay, this for liquid. And here the solid form. Okay, that again in solid form we have many options. Three options are there. Okay, so it can be stored in a the carbon nanomaterials. Okay, then it can be, then some of the alloys we have, lanthanum based alloy, magnesium alloys, titanium alloys. Some alloys are there which are having a huge potential to capture. Okay, it's very simple. Means if there is a flow of hydrogen, and if you expose those gas to these materials, it will simply capture, because they're having a affinity towards the hydrogen. It will capture the like we are using the sponge to capture the water. Simply capture that one. It goes to the sites and it can be stored for long time. It means once you want to store it for months also, once you store it will be in the same form. Until you provide heat to that material, it will not release. It is safest mode and long term also. It is very good for transport. So here the high risk will be the transport. When you're going to transport high pressure hydrogen here and there will be a huge risk of explosion. When we stored in this form, so we can able to capture in a solid form and there will be no leakage. So for transport, it will be a good option. Okay, so these are the some applications of hydrogen, because nowadays everywhere we're thinking about the uh, hydrogen. So here the last option, if you see, we mentioned green sustainable building also. So that goes much towards the we can able to have the HVAC air conditioning with hydrogen. Okay. Plus, I'll tell you the near future, it will be very shortly, it will come in the place of LPG. Every home we're going to use hydrogen. So that part also people are working in such a way that the LPG will be replaced by the hydrogen and we'll be going to use our burners with the hydrogen. This video, so videos are not working. Just escape and play. This play will be there. Just go to the photo, play will be there. No, just escape and go to the picture. There's a play button will be there. Huh. Okay, it's not working. So here the video will be showing how fuel cell works. Okay, that video. Okay, that will tell the how fuel cell will work, how we are supplying hydrogen and oxygen from different, and it can able to produce electricity, that is there. The second video, this I was keeping that video for IC engines, how we can able to use IC engines using hydrogen. Okay. Okay, so anyway, these are the two options as I'm mentioning from beginning of my talk. We have this good two applications for onboard applications. We can use fuel cell and for combustion process. Okay, so in both the cases, maybe next slide. Here also you can able to see this is an example of onboard application. Okay, so this is a real picture what I captured from the video. It is a exhibition video was there. I think this is Hyundai. Hyundai has done some exhibition. Okay, so this is the vehicle they already manufactured. Okay, which is running with fuel cell. This portion is the fuel cell stacks. The fuel cell is there. And these three cylinders, if you see, these are the type 4 cylinders in which we are going to keep hydrogen at very high pressure. Okay. And once we have the gas available, which can be sent to the fuel cell stacks or maybe IC engines, and we can able to run the vehicle. So here the important thing is what I want to means emphasize more is the compression here. So here easily I am showing here in this picture that we can able to use high pressure of 700 bar pressure to the fuel cell or IC engines. The important question here is how we are going to compress it. Because again, for compression of the hydrogen to that much high pressure, if we are again going to use the electricity, the energy which is coming from the fossil fuel, again, this vehicle is not a green vehicle. Again, our electric vehicle, if you're charging in the slot which is coming from the steam power plant, okay, so that vehicle is not a green vehicle. So only by using the electric vehicle, we cannot say it's a green vehicle until the energy source for that is also coming from the electricity, which is coming from renewable sources. Okay, so same here, I'm going to use hydrogen to run fuel cell or engine, but for compression of that hydrogen, if you're again using the fossil based energy, then this vehicle is not a green vehicle. So here I'm going to discuss the process, how we can able to compress the hydrogen to such high pressure without using electricity. Okay. So next. Okay, this again one picture just showing the cycle, how from start of hydrogen to the application it will work. Will produce, store, store in a solid form, then compress in a solid form without using electricity, then stored in a high pressure tanks and the fuel cell. Okay. So this is the system I'm talking about the. So here, as I mentioned, we have the materials, such alloys I told you. Those alloys are having a tendency to absorb hydrogen. That is the first thing. So first of all, that can be used for storage. That is a good thing. Now here, how we'll compress here? You can see this graph. This shows that how it is absorbing. So once it is absorbed by the material, okay, at low pressure, is at low pressure. So at low pressure, we are supplying the hydrogen to the material. It absorbs at low pressure. And if we are giving the heat to the material, okay, it may be a solar heat, it may be industrial waste heat, whatever the available heat we have, we can able to compress the gas to very, very high pressure. That is the process happening in this material. So such materials are there in such a way, they're having a tendency to change its equilibrium pressure to very high extent with a small introduction of heat. Okay, so we have different class of materials. One class works in such a way we can able to use as a compression for compressor. So here we are not going to use any of the mechanical compressor. Here, the available heat can be used to compress to high pressure. An example I'm going to show here in the next slide. In our lab, we have tested one of the compressor. These are different types of compressors available right now. Some are mechanical, some are not mechanical. When we say mechanical compressor means it is having, it will be always going to use a large amount of electricity. Okay, because for compression of any of the gases, it needs a huge amount of electricity. So when we go for any of the mechanical compressors, it will be having more energy consumption, and there is a huge maintenance cost. If you go for the non-mechanical, any of the non-mechanical, the requirement of energy will be very, very less. So that will be, in that case, it can be a preferable to have a green compression. So green production, green application, in between we should also have green compression. Then only the full cycle will be a green cycle. Here we can able to see the volume covered by the hydrogen at different category. If it is gaseous form, this much amount of volume is required. When you go for solid form, the same mass can be stored in a small volume. Okay, so that big cylinder can be stored in a small volume. So it will be compact and easy to transport. Then once we have stored, we can integrate with the any of the application. Okay, so I'll just keep this what about the metal hydrides. It will go for long time. Okay, so it is just brief. I'll give you just kind of a material, okay, which can able to store hydrogen and can able to elevate the pressure up and down. It can able to change the working temperature and pressure also. Okay, so that I will skip for now. Better this. Let me just keep this. Okay, so this one of the this also video, it is not working. So here in our lab we have a small scale compressor we have built, okay, to test how this technology will work, and we can able to compress or not, and it will compress to what level. Okay, this is not working, but the photo is there. This photos you can see. So this much big compressor we have built. The photo is there. This is the middle one is the real photo, and here we have uh, the contour diagram for structural and thermal analysis. Okay, so we have designed using for its structure. Structure means we designed this compressor to sustain for 400 bar pressure. Okay, so we are going to compress our in our lab. We tested till 270 to 80 bar pressure. So we have designed this for 400 bar pressure. Okay. So here you can see the performance. Okay, just this curve shows that how the material behaves at different pressures. Okay, for example, this yellow, if you see, when we absorb the gas, okay, at 20 degrees Celsius, okay, when we are keeping the material at 20 degrees Celsius, we're supplying gas to the material, it can able to absorb at around 10 bar. Around 10 to 20 bar pressure is sufficient to fully saturate the material. Now, when you're heating the material, okay, so as per the availability of the heat, it may be till 80 degrees Celsius, 100 degrees Celsius, 140, 150. So last you see 140 degrees Celsius, when we heat the same material, the closed system, when we heat the closed system to 140 degrees Celsius, the pressure which can able to elevate here is almost 270 bar. So the 20 bar of hydrogen, we can able to compress to 270 to 80 bar pressure only with the supply of hydrogen, the heat, okay, just because of such kind of material we are uh, using. So this is the real readings what we got from the our experiment. Here you can able to easily see this last one at 140 degrees Celsius, the output pressure we achieved is a 270 bar. So we supply the gas to 20 bar and we can able to compress to 270 bar. So here this system can able to completely replace the mechanical compressor, and we can solve the problem here for the energy consumption. Okay, because if we are keeping the hydrogen at low pressure, we cannot able uh, to have more mass. If we don't have more mass, the production of energy will be very, very less. So it is not like that we are going to run our vehicle for some kilometers, again we are going for refilling. Okay, so it should be refilled in such a way, it should go for the sufficient distance, then we should go for the refilling of gas. So that's why it was proposed that it should be minimum of 700 bar pressure for onboard application. So this we have done experiments to just understand how this compressor will work. Then we extend this work to predict if you go for multi-staging. This is single stage. In single staging, we achieve this pressure. Then for to predict multi-staging, how much pressure we can able to achieve, we have done the 4-stage compression. This is 4-stage compression, and here through simulation we observe that this is the pressure. The pressure is going till 700 bar. So if you go for multi-staging, If you go for the 4 stage or 5 stage, and the temperature range from atmospheric, we are heating to only 150 degrees Celsius, we can able to achieve 700 bar pressure. So in that way, we can able to reduce the requirement of energy. Okay. In the next table, I'll show you the comparison. This shows the comparison between the for same amount, okay, for same production rate and same capacity, the non-mechanical or mechanical compressor, how it will cost. Okay. So you see the investment cost, okay, we can say almost same, but here the maintenance cost will be very high in the case of mechanical compressor, because in mechanical compressor we have the moving parts. Whenever we have the moving parts, there will be always a chances for the mechanical maintenance. And in this case, it is thermal compressor. There is no moving parts. And here the energy requirement will be very, very low. This, because here in this case, the thermal compressors, we need energy for sensors, the temperature sensors, pressure sensors, flow rate sensors, but we are not going to use energy only for the compression. So here the huge difference can be seen from here. So this is about compression. Then we have okay, I'll restrict to my time. So we have different other applications of such materials, because once it is stored in a solid form, then we opened multiple options. We have multiple applications we have. So like one of the application is here, as I told you, now we are going for to integrate our power plants with the solar power plants. Okay, so we can use solar energy, solar thermal for steam generation in a steam power plants. But again, in the evening and night time, that will not work. So the here solution is we can able to store the solar thermal in some form, like people are testing phase change materials to store energy for the evening time. So here, if you are using such materials, metal hydrides, we can able to store a large amount of solar energy, and we can able to produce the huge amount of heat that is sufficient to produce steam. So that still work is going on, and many of the industries, they are installing this there in the underground storage for producing heat for the as a supplementary heat for the steam boilers. Okay, so these are different applications. I'll just keep, will not discuss more. So these are the possible uh, applications. When we stored in a solid form, then we have multiple applications. Like one of the application here, we have the purification. As I told, these are the materials having affinity towards only hydrogen. So in some of the production method, if any other gases also produced, so that mixture of gases, if we are supplying to the these materials, it will only capture hydrogen. Then we can able to extract only hydrogen. So in this way, we can able to use this as a for purification also. Okay. These are the technologies. I'll not go much detail. This is, you can able to see the purity level in the case of metal hydrides. Okay, how much purity we can get, and it can able to also work at low pressure. That's a good thing. Then we have air conditioning. Okay, this can also be used as a air conditioning. Okay, just I'll give a brief about this for air conditioning. This is my team working with me. So air conditioning, how it works, air conditioning is, as when these materials absorbs hydrogen, it releases heat. That is a exothermic process. Then when I want to take heat, when we want to take the gas out from the material, we have to supply heat. That is a endothermic process. So if I am making a pressure difference in such a way, we can able to extract the hydrogen from the material without supplying any heat. What will happen? It will start taking heat from the environment. So the space where we want to produce air conditioning, if we are putting a material and by making a pressure difference outside, if you extract the hydrogen from the material, it will start absorbing heat from the room. In that case, we can able to produce the air conditioning in the given space. So I'm sorry, I have skipped many of the details for many of the applications. If you want to know about that, we can discuss here. Thank you.
The floor is now open for questions.
Vinod Kumar,
Yes, sir.
excellent presentation. Regarding hydrogen production, you said about electrolysis. Okay, what kind of the electrodes are used, and which one is suitable, most suitable for efficiency?
See, now the for commercialized application, mostly people are going for the PM electrolyzers, PM or AEM. Okay.
What is PM? I just
forgot the full form. The AEM is alkaline based electrolyzers, and I just keep the name. Yeah. Yes.
Regarding storage, you said hydrogen will be absorbed by the material.
By the materials.
Storage. Okay. So in the case of absorption, what kind of the complex or compound formed in the metal? Is there any place to occupy or store?
See all the materials we have, if we study the structure, all the materials are having that vacancies. The interstitial sites are there.
Which sites?
Interstitial sites.
Interstitial sites. Okay.
So those materials which are having the size of that space to accommodate a atom, H2 atom. So H2 is not going as a molecule. So any of the material having that much sufficient space, okay, that can able to absorb the hydrogen in a atomic form.
Okay, atomic form.
Yeah.
If more hydrogens are developed, this may lead to hydrogen embrittlement.
Yes.
Okay, so
that is the other case. I'll tell you, sir. Sorry for interruption. So here we can talk about the two different systems. So when we talk about the storage of hydrogen in a solid form, so here we want to choose a material which can prone towards the embrittlement, because then only it will get absorbed. Other side, if you want to see, if you want to make structures like pipelines or any components, in that case we have to use a material which should repel the embrittlement. So embrittlement is good here because here you want to absorb the gas. In this case here it is not good, because here we want to make a structure that should not undergo embrittlement, that may increase the life of the system component. So here we need embrittlement.
So in which case, which is suitable metal for this?
For absorption?
Absorption.
So see, if you want to go for high storage, then magnesium based materials are good.
Can you quantify the amount of hydrogen?
Yes, we can quantify. This setup we have, I skip that.
Based on the materials property, materials aspect.
Yes.
Quantify?
Yes, we can. Can you open this slide? So we have in IIT Calicut, we have a setup. Okay, any kind of material, if you have, even if you are unknown to that material, if you don't know the material type, that also we can able to test whether it is absorbing or not, and also it absorbs, how much it absorbs. That setup was there. This setup. So this setup is there, that is used to quantify the amount of hydrogen stored by any of the material. Even if you have unknown materials also, we can test here to find out whether it is suitable for storage or not. And if it's suitable, how much quantity can absorb in a weight basis. So per kg of material, how much grams or kg can be absorbed. Like when you go for the magnesium, as I told, so 1 kg of magnesium, okay, that can able to store around it is 7.5, 75 to 80 grams at high pressure it can absorb, at very high pressure. Yes, sir. Thank you, sir.
For storing hydrogen in that solid form, is that metal hydrides the only, like in the present research, are the metal hydrides are the only option, or some?
Can you open it? We have 3 types of options stored in a solid form. It was there. I skipped that also. When we have in the carbon materials, this here I have shown. What happened? Okay, we have 3 options. We can use carbon materials here. Yeah. See, we can use carbon materials. Okay. So carbon materials are having a good storage capacity. Okay. Like carbon nanotubes, carbon fibers, graphite, graphene. But regenerative is very less. Means this option is less compared to the metal hydrides. Then we have metal hydrides. Then we have complex hydrides. So metal hydrides and complex hydrides both are same. We call it the complex hydrides because the reaction happens in more than 1 or 2 stages. In the case of metal hydrides, it's very easy. In a single step process, and it's very easy to store. So we have many options.
I think this metal hydrides and complex hydrides, they will not be available in that form which are to be used to absorb hydrogen.
No. It's available. Means the same alloy we can use. Before using, we have to activate it. So activation is like heating at high temperature and purging of hydrogen at high pressure. This activation process. Once you activate it, it can be used. So in the same form, as some names I mentioned, LaNi5, ZrMn, MgNi. So those are in the same form it's available. Means in the commercialized, it's available. And many of the labs, they are making their own new material to increase the storage capacity.
Point I wanted to make is like you are making a new material. Suppose you're making it a form so that it can absorb hydrogen. So actually you're expending energy, but
Yes.
you have not quantified at how much
No.
energy is
Correct. Yeah, again, here we are putting our effort to make such materials. That's correct. So as this form is not available, we should be make it.
So basically, like what we should progress in further research is the energy, suppose X is coming and Y we can obtain from hydrogen. So Y should be greater than X. So I think that should be the.
No, see, this is actually a simple alloying process. If means the people working on metallurgy side, they know this ball milling and this alloying, this basic alloying process only. There's no much technology required here. So if you have number of different elements, by only going for the alloying methods, melting and alloying, it will be easy. The arc melting is the best option for this. If we have arc melting facility, we can make these materials. So there's no much technology is there, but some effort is there to produce the material. That is fine.
Okay, thank you.
Actually, we discussed about the storage issues, and because we need more hydrogen to burn to get an amount of energy. Okay, so we have these issues in storing it and compressing it and all. So where this research is actually concentrating on to mitigate these issues or integrating this fuel cell, this hydrogen energy with other green energy solutions, where the research is actually more concentrating on recently. Because I think these hydrogen fuel cell vehicles, ultimately they are electric vehicles. Am I correct? Yeah. Thus, electric vehicles are actually, they are not depending on hydrogen fuels only, because I think the new release on electric vehicles, they are using lithium-ion battery also with this fuel cell, because they are considering these vehicles, this fuel cell, hydrogen fuel cell as an extender only, I think so. I don't know I am right or wrong.
Correct.
Yeah. Then where this research is actually concentrating on integrating this with or other renewable energy solutions or mitigating all these issues relating to the storage and all.
Integration is not a issue. It is very easy because just we are integrating 2 different technologies, because in fuel cell we need supply. Here we have metal hydrides which can able to supply. So that is not a issue integration. The work needed here is the storage. Okay, because how to increase the storage capacity. Because if you want to use such materials for on-board application, it should able to store large amount of hydrogen. That is the important thing. So here again, like sir has mentioned that we should have, we should go for such materials which can able to absorb large amount of hydrogen. So here research is there. Integration is not a problem. That is easy only. Yeah. Thank you.
I think the first time I'm getting to know that such storage option for hydrogen. Thank you. This bomb threat still remains?
Yeah,
Or,
because if we are very careless to that safety, because the leakage is the main problem. Like in our lab also, we are using all standard equipment. Still, we are putting a lot of sensors. For small amount of gas also it leaks. It catches fire and it's gone. That is the main threat. Still, it is there. The only thing is the design what you're making. That design should be in such a way this leak proof. That's the only option. Yes, sir.
The topic was hydrogen fuel cell for marine vehicles. Or have you done any?
No. I don't work on the marine or fuel cell.
Okay.
I just mentioned that before fuel cell, the things are there. Might focus on that side.
Okay, and I just wanted to know if I have to put these solid state storage on board marine vehicles, then what will be the weight of
No,
solid state storage that I will need to carry on?
I will not suggest this for onboard storage application. That's why I shifted my talk towards the compression. So you stored in a gas form only, but for compression, this can be used. That's what I'm saying. So I'm not suggesting for that, because if you go for storage, it will lot of weight is required. Because I mentioned that 1 kg of material absorb only 75 grams. So if you want to store H2 in a kgs, you have to go for some thousands kgs of the material. So storage on board is not good. Storage stationary is good. So stationary power plant is there. There we can keep large amount of materials, store it. But on board storage is not good. On board, we should have the only compression application. So compress somewhere else. The compressed gas we have to put in a on board. But storage, stationary applications we can use. For power plants, if you want to produce electricity through fuel cell, so we can store at a high amount in metal hydrides, supply the gas and produce electricity. Not for on board.
I'm sure there are many more questions. I'll ask one. You have told us how to store it. After you store it in the metal hydride, is it easy to take it out of that
Yes,
and use it
once we supply heat, it is a reversible process.
in a controllable way so that
Yes,
I
yes,
will
yes,
I will
yes,
get
yes.
it at the rate that I want?
No. We can control the rate.
Fine.
But again, after releasing, when you're keeping where,
Mhm.
that is important.
And there's a certain capacity for, let's say, 1 kg of metal hydride.
70,
And
70
how will
grams.
I know how much it has stored? Is that just by measuring how much I feed to it?
No. First, we have to go for such studies to find out the. I shown that setup now.
Okay,
So setup can be used to test the material.
fine.
From there, we can able to find out.
Okay.
the
Thank
capacity.
you very much, Professor Vinod Kumar Sharma. Very interesting talk. I'm sure many more have questions. Thank you very much.
Yeah. Thank you. Thank you so much.
Thank you, Dr. Vinod Kumar Sharma, for your insightful presentation on hydrogen fuel cells for marine vehicles. We greatly appreciate you sharing your knowledge with us today. I now invite Session Chair Dr. D.D. Ebenezer to kindly present a token of appreciation and a certificate to Dr. Vinod Kumar Sharma. Sir, please.
We have now come to the scheduled tea break. Please feel free to enjoy the refreshments provided. We request everyone to reassemble by 11:15 as we will resume the next session promptly. Thank you. Before tea break, there will be a group photo. So everyone please remain.